It turns out photons are even weirder than some of the quantum mechanics that we've looked at earlier. They're both a wave and a particle. Sometimes we prefer to say that they act like particles. Sometimes we prefer to say that they act like waves. They're actually both. And depending on whether we are looking at the wave function or the particle function, we use different kinds of terminology. So the easiest way to think of these is as electromagnetic waves. The way we measure waves is we measure them from crest to crest, and this is called one wavelength. It's symbolized by the Greek letter lambda, which looks like a little L. Lambda sounds like L, and that's because it looks like an L. So this Greek letter lambda is L, which is a way of abbreviating the idea of wavelength. So if we measure from trough to trough or from crest to crest, either one of those methods gives us one wavelength. So a higher energy means that there's a lot more of these crests coming in. There's more vibration or a shorter lambda. So the electromagnetic spectrum consists of all the different energy levels that these photons might occupy. If they have a low energy, as shown at the top of this diagram, then they have a long wavelength. So these are called radio waves. They have a wavelength of maybe 100 kilometers or 10 kilometers or 1 kilometer. That's what's shown here on this table. So AM radio waves, for example, have a wavelength of 1 kilometer. They're very low energy. They have a very little ability to penetrate through things like freeway overpasses, which is why an AM radio on your car cuts out as you go under an underpass. Then as we increase the energy, the waves become shorter and we get into shortwave radio and finally into microwaves. And microwaves are able to penetrate into things. That's how microwave ovens work. As those higher energy photons, now with a wavelength of, let's say, 1 centimeter or 1 millimeter, as those higher energy photons penetrate into your food, they give that energy to the food, and that food heats up. And so if you happen to like Hot Pockets, this is how a Hot Pocket works, is by giving that high energy photon gives its energy to the food that you've put inside the microwave. Then as we go to shorter wavelengths and higher energy, we end up with what's called the visible spectrum, which is actually a fairly narrow part of the entire electromagnetic spectrum. Lower energy red, higher energy violet. The mnemonic for this is the supposed discoverer of electromagnetic energy, of the discoverer of light. Of course, no one discovered light and everyone at the same time. We say the discoverer of light is Roy G. Biv because we go from red, orange, yellow, green, blue, indigo, violet. R-O-Y-G-B-I-V, or Roy G. Biv, is supposed to be the discoverer of light. We have higher energy photons in this electromagnetic spectrum. Then we end up with ultraviolet. Beyond ultraviolet are X-rays, and the highest energy photons that we might come into contact with in the universe have a very, very short wavelength, very, very high energy. They're called gamma rays. This is just showing the same thing, but instead of sideways, we've turned it 90 degrees. So we've gone and just taken this visible spectrum and turned it 90 degrees. So we've gone from up and down to left to right on these slides. And so now we're looking at the visible light spectrum. We've got the lower energy now on the right-hand side, the higher energy on the left-hand side of this slide. Smaller wavelength on the left-hand side, higher wavelength, larger wavelength on the right-hand side. That's what's shown by this wave here. And so in this spectrum, then we go from going back the other way from highest energy gamma rays to slightly lower energy X-rays, to slightly lower energy UV light, to lower energy visible light, to lower energy infrared, and then even lower energy radio waves. We use these higher energy photons in the X-ray part of the spectrum in medical imaging. So this is what we use when we actually take an X-ray. Because these have a great deal of energy in them, they're able to penetrate through tissue better than visible light can. Bone, because it's dense, as we'll learn later on when we get to the bone module. Bone is dense, and so it tends to stop these high-energy photons. Other tissue, like lung tissue, is less dense, so it doesn't stop these high-energy photons. So areas that have bone show up as white on an X-ray or whiter. Areas that have no bone and just lung tissue show up as dark areas on this X-ray.